Hi, I'm Bennett Alterman, and today we're going to discuss Newton's second law as described by the motion of a falling tissue. So the objective of this lab was to simulate how Newton's second law works by observing the motion of an object that is dropped from rest and falls somewhat slowly straight down. What I did was I dropped a crumpled up tissue. The system included solely the tissue, and this tissue had a mass of 4.8 grams or 0.0048 kilograms. I've labeled my positive x-axis to the right, my negative x-axis to the left, my positive y-axis up, and my negative y-axis down. I've also included a length bar of 1 foot, or equivalently 0.305 meters. The forces and interactions at play here are gravity and, later as we'll see, drag. Here I've made free body diagrams, both with and without drag. On the case on the left, without drag, you'll see that the force net is equal to weight, or gravity, which is negative mg, or negative mass, times gravity of 9.8 meters per second squared. On the right, with drag, you'll see that force net is equal to the weight force plus the force of drag. Here, again, gravity is the weight of negative mg, and the force of drag is negative b, which is a proportionality drag coefficient constant, times the final velocity. Please note, however, that a different drag equation is going to be used in our computational model that we'll see in a few minutes. Here you'll see the actual tracker data, where my tissue falls in the negative y direction. Here's the actual graph and data that I've obtained from my tracker video. The important equations to note are, again, Newton's second law of V final equals V initial plus F net over mass times delta t, as well as the drag equation of negative b times final velocity. Again, this equation is not the one we will be using in our computational model, as well as force net equaling the weight force plus the force of drag, as well as weight equaling negative mass times gravity. Here we can see in the computational model without drag that I've given the ball's mass 0.0048 kilograms, and its both initial position and velocity are at the vector 0, 0, 0 at time 0. I also have a time step of delta t being 0.0333, which I've obtained from tracker. Here we have a total time of 0.6 seconds, again obtained from tracker, as well as the equation for weight, which is the negative mass of the ball, times gravity multiplied by j hat, which is our direction vector, in this case the negative y direction. Here you see again that the net force is equal to solely the weight. We've also updated both the ball's velocity and position by multiplying by delta t. Here you'll see this model in action. Notice again that the ball is falling in the negative y direction. Here we have a computational model that takes drag into account. In this case, we've inserted our proportionality constant b for drag force of 0.024. We've also edited our force equation to be the b constant times the magnitude squared of the ball's velocity times, again, our j hat direction. Here we'll also see an arrow scale, which was calculated by a height of 2 meters divided by our mg, of which equaled 0.057. And these arrows both have tails at the origin and move either against gravity or with gravity, as we'll see in a moment. Here we can see the model that takes drag into account. You'll see that the yellow arrow pointing downward represents the weight force or gravity of negative mg and remains constant throughout the entire model, whereas the blue arrow pointing upward indicates the drag force, which begins small and increases in magnitude as the ball continues along its path. Here what I've done is I've taken my data from both the observed tracker data and the models both with and without drag and computed one graph containing all three. You'll see here that the observed tissue correlates very closely with my modeled drag system. Does this model accurately predict what we saw? The answer is relatively. Why, you might ask? The falling tissue is changing directions near the end of its path due to the drag force. This causes a slight change of position that is not entirely in the y direction, causing this tail that you see at the end of the graph. What does it mean? Which models predict terminal velocity? The answer is the model with drag. Without a balancing factor for negative mg with drag force, the tissue would continue to accelerate downward infinitely. In case 2, we imagine that the object was initially thrown downward instead of just released. Here, the terminal velocity in physics terms would remain the same, as is the fastest that object can travel in that direction. In terms of what we saw between releasing the object and the ground, the final velocity would be higher due to the added force and therefore increased acceleration.